So my name is Denis. I work at GridGrain Systems as a client service lead. How many of you know about GridGrain or Apache Ignite? All right, nobody. Perfect. So I need to make a kind of introduction of what it is. Well, basically, that's an in-memory data storage. So that's a data grid with transactional consistency and some additional functionality built on top of that storage. Everything is kept in memory and it's sharded across multiple nodes, so you can scale your data like in a cluster. It's written in Java, but it has integrations like with external data storage and support of SQL. We'll come to that. I'm not going to pitch you GridGrain like not only. So we'll see how you can boost your Postgres installation without use of GridGrain, and when we come to in-memory data grids, we'll see that in more details. So this is going to be our agenda. Somehow it doesn't. Oh, here. So this is our agenda for today. It's first we'll see how you can benefit from caching. What is the caching in the first place, and how to make use of it in your current, if you have Postgres installation, how to make it work better, faster, and decrease your latency of your operations. Then we'll go to some sharding solutions. If you want to store more data than one single node can fit. And well, finally, we will go to in-memory data grids and see what GridGrain is and how you can use it, even though if you only use Postgres, how you can make it like work faster together, integrated with GridGrain. So let's start everything. What's happening? All right. Yeah. So let's start with caching techniques. So we'll see what's the idea of caching. The idea is to preserve some hot subset of your data in a more performant and usually more expensive data. For example, if you have disk storage, then it's you'll probably have a more expensive and smaller set of memory, which is faster, and it's better to keep the most required data in that layer, in the memory. And this is what the idea of caching is about. There is a table that goes over the internet. Like in the middle column, you can find the latency of some operations. You can see on the top row the time of one CPU cycle, like on average, and further you can see like what are the latency of different access times to different data storage kinds. On the right column, you can find the scaled latency. Like one CPU cycle is taken for 1 second, and you can see how it's related to how different kinds of data access is related to one CPU cycle. So as you can see, as you go to memory and like memory-centric solutions, you stay in nanosecond latency, and this is where you want to aim at. It's like you're not going to take into account like cache. CPU cache latencies, like when architecturing a huge system, but the memory, you can actually benefit from storing data in memory. For example, like if you have just doing some memory lookup, it's like 100 nanoseconds on average. You can also make use of Intel-Optane, which allows you to work with your persistent data, but within the nanosecond latency. It's like a great technology, but I'm not sure that it always performs perfect with all the workloads. For example, I'm not sure about the latency with random access, but you can actually achieve this kind of latency latency while working with disk. But as you go further, if you move to accessing the disk, you lose this kind of kind of latency. You go in a scaled in scaled terms, you go to hours from minutes, and this is huge. And so the idea of caching is to keep as much like needed data as possible in memory. And you don't actually need to use any external tools to achieve that. It's always available in Postgres. There are different techniques to achieve that. For example, if you do a lot of related queries, like if you do a query over and over again, you can just remember what's the result of that query. Not to go to Postgres again to request something, but just remember that if you request this data, that's the result. The downside of it is that if data changes, then you need to invalidate that cache, and sometimes it's hard to tell which cache records you need to drop if you change some certain data records. So you need to introduce some kind of expiry or something like that. So it's doable, but it's kind of naive and simple to implement. Another thing is query plan caching, which is implemented inside Postgres. So if you run some complicated query, and there are different steps of that. First, you build a query plan, like you parse the query, you build a plan, and execute it. So the part where you build the query plan actually takes time, and instead of doing that over and over again for the same query, you can just memorize it and preserve it in memory and use it over. It's done inside Postgres. It's configurable and achieved using just configuration, but that's a technique that can be used not only in Postgres but in any SQL database. And the most interesting part, as I would say, is the relation caching, or data caching or index caching. That's the caching of data pages that are used to actually produce the result of your queries. So when you execute a query that needs some data from disk, then the database will go to disk, pull some information to memory, and if you do something related to the same data set again, then you don't actually need to go to the disk because you already have this information available in memory. And this is also configurable, and you can make use of it when tuning performance of your database. There are two kinds of approaches for Postgres. Postgres itself has a shared buffer, which can be configured to make the data pages be stored in memory and not offloaded when you finish using the data pages. And another thing is OS buffer that kind of doing the same thing but on a different layer, not on the application layer, not on the Postgres layer, but on the OS. Operating system itself caches the pages that it reads from disk, so you don't need to go to the disk again every time. Here, what are the tricks? It's hard to find the perfect ratio between these caches. For example, OS buffer is enabled all the time, and the size of it is defined by the amount of memory that is not used by other applications. You can try running more applications to see how your performance of your database degrades when you get less memory in page cache. And you can read up about the shared buffer, and it's said that you rarely get much improvement as you go beyond 15% of your memory if you give it to shared buffer, because Postgres utilizes the OS level buffer. So there are many things that you can change here. Like you need to experiment and see what works best for you. So you need to spend actually some time to find the perfect ratio here. And yeah, it has nothing to do with scaling. It's just improving the latency, the performance of your queries that you run on a single machine. You can configure perfectly your one machine, but as you go further, you will see that you kind of to buy better machines, to buy better equipment is much more expensive than like just buying more machines that have the same performance, but they actually scale and they distribute the load across multiple nodes. So let's see what are the options if you want to actually scale your data across multiple nodes. First, let's see what kind of requirements we put to our system. First of all, Postgres is a strong consistency ACID database, so we don't want to lose these guarantees. We don't want to give up the ACID guarantees. So otherwise, it will be a different kind of product. We still need the ACID guarantees. Also, if you store data across the cluster, you need to be able to actually use it to benefit from it. So load balancing is also required. And when you have more than one node in the cluster, then the chances are that more node failures will happen because you have more moving parts. And here, some kind of failover would be handy. Let's see. Well, there is a solution for a part of these requirements. It's a PG pool. That's basically just a replication between different instances of Postgres. If you have like one installation of Postgres and you perform some operation on it, you can just set up the same instance and configure the replication between them. So if you change data in one instance, then it will be transferred to another. Here you can perform writes only on one part, and it will be transferred to another. So you don't scale the write operations much, but for reads you can use actually both copies. And here there are like different configurations. You can set up, for example, synchronous replication, and in this case you will need, in order to finish the operation, you need to go to both instances and to change the data there before you finish. So you can actually get an overhead for writes, but you get a failover because if one of the instances fail, then you can use another one, and your reads operations can be load balanced across different nodes. Here, another downside is that you don't increase your total capacity of your system. It still stays the same as a single node because both instances will have the same data set, and you don't distribute your data across multiple nodes. But if you want to address that issue, then there is another solution. Actually, there are like multiple of them, but in general they look pretty similar. There are products like PostgreSQL, Excel, or Citus Data, which has been acquired by Microsoft recently. And as far as I know, there was a speech this morning by somebody from Microsoft. I guess the speech was about Citus Data. I wasn't able to join that presentation, unfortunately, but I guess it was something about that. So here you have the architecture drawn like that. Yeah. Yeah. There is a hyperscale product in Azure, and that's why Microsoft acquired Citus Data. So idea behind PostgreSQL is you have data nodes. Those are just like Postgres instances, and on top of it, you set up additional infrastructure like coordinators, transaction managers, load balancer, and in total, it gives you all the guarantees that we wanted to achieve. It gives you ACID, load balancing, and if something fails, you have multiple instances of the same thing, so you achieve failover. It supports sharding. If you see that you hit a limit of your single node capacity, then you just add more nodes, and you are able to store more data in your system, and that's as simple as that. The downside of it is that it's hard to set up, really. If you go to documentation of PostgreSQL, the first thing they write in the tutorial is that it's going to take some time to configure that. What it means is that it's painful. Like you need to actually spend a lot of time, and it takes like a DevOps team to keep it running, and there is a lot of configuration required to run it. And that's not purely in-memory technology. So sometimes you'll get latency spikes because you need to do some page replacement. You need to go to disk and read data that is missing in the memory. So you also need to configure the data nodes themselves properly to make them work in an optimal way. So it's a good solution, but it requires a lot of time learning about that, and maintenance is pretty tricky, but it's good enough. Yeah. So finally, let's go and see what GridGrain can propose here. If we have a Postgres instance, and it's either can't fit enough data into itself, or it's not performant enough, which is usually a case when customers come to us, and they quite often say, well, we have a relational database and it's not performant enough. Help us somehow improve it. So this is how we work in this situation. This is what Apache Ignite and GridGrain is. The middle section is about what are the parts, what Apache Ignite is. The red square is, you can see that it's on the basis layer, it's an in-memory data store, a distributed one, and on top of it, there is a bunch of APIs available for your application. There is a key value API, SQL, you can set up services or perform computations. So everything is built on top of the basic layer, the in-memory data storage. Under that, you can configure an external storage. For example, it can be Postgres, it can be your mainframe that you're using in your system, or it can be Hadoop, or it can be native Ignite persistence, because there is support of a native persistence. So you can actually configure something that works with disk. It can be a relational database. It can be a native one. So there is such possibility. And the blue squares is what GridGrain proposes. So there is some functionality built on top of Apache Ignite, such as data center applications, snapshotting, security, and so on. We're not going to talk about that too much. That's just an introduction what GridGrain is about as a product. So how you can make use of it in your system. For example, you have some storage layer, your Postgres installation, and on top of it, you put the caching layer, which works purely in memory and is sharded across multiple nodes. and you use it in your application. So you do a kind of migration to use the Apache Ignite instead of your Postgres, and the Ignite will go to Postgres and request data when it's needed, or make updates. That's one of the ways how you can do the migration. Another way is just enable Ignite persistence, pull the data into Ignite, and kind of forget about your old data storage. That's also doable. Usually customers go the first way because they are not comfortable enough when they see the new technology, and they can't trust all their data to be stored in a single place. So usually they start with a caching use case. When they get comfortable enough with that, they just migrate everything to the disk. So here's how the interaction happens. You have some data set. It's spread across the cluster. The middle section is the GridGrain cluster. And if something is missing in that in-memory storage, then Ignite can go to the external storage and make a read-through request. That's read-through semantics. If some key is missing in the caching layer, it just goes and then it takes it just the usual way from the data storage that you configured. If you change something there, then the caching layer can go to the external data storage and change it there as well. It's configurable. It can be, this behavior can be tuned. You can batch updates and write them not one by one, but in a batch. This behavior is available. You can not even enable it and just work in memory by loading the data first and keeping it in memory. But that's the idea. And also there is support of SQL. It's ANSI 99 compatible. It doesn't have all the specifics that Postgres have, so a kind of migration will be required. But well, usually it's not a huge deal. But yeah, you need to keep in mind that all the queries will probably need to be tuned somehow to make it work perfectly with Apache Ignite, because it's a distributed data storage, and everything that you keep on a single machine, all the queries that you run on a single machine, not always map perfectly on a distributed storage. But some basic SQL functionality is available. Yeah, well, what's important to know about distributed storage is that you need to take care of data collocation. If you, for example, have tables of cities and countries, it makes sense to keep all the cities from the same country on the same node. So you need to make somehow related data be stored on the same nodes. Otherwise, you'll need to make a lot of cross-node requests to do some like a business level request. It's true for any distributed system. As far as I know, Postgres XL also does this kind of collocation, and it's yeah, it's pretty important to make use of it in Apache Ignite as well. This is how the processing, the processing of request is implemented. First, the node that did the request builds the execution plan, which will contain two parts. It's a map and reduce. Like map requests are sent to the nodes that store the information. This query is executed there, returned to the reducer, and the final result is produced and returned to the user. And so it's kind of like a map-reduce fashion. If you don't configure the affinity collocation properly, you will need to make cross-node requests on the map stage. So it will be like a lot of communication between nodes. So it's important to make sure that all related data is stored together. Oh. Yeah, and it has transactional guarantees. It has strong consistency. It's yeah. If you're curious, you can look up how two-phase commit protocol is implemented. We have it in Ignite, and it works even with external data storage. So yeah, you can have transactions if one of the nodes fail and can't write something to the storage. Yeah, you can roll back transactions. So all the guarantees that normal ACID databases provide, they're also available in Ignite. But it's mostly like available in Java API. The support for SQL is on its way. We have it in beta. It's not like production ready. We are finishing it up, but yeah, we implemented MVCC, some multi-version concurrency control that allows transactions for SQL, but well, currently we have non-transactional SQL. You need to keep it in mind. So you need to either make some lock-in or just to use the Java API, which is like a perfect replacement for SQL. And yeah, if you have external database and it's transactional, then we will make use of those transactions as well. So coordinator of the transaction will first go to the external database, write the information there, do the transaction on the cluster, and yeah, if something goes wrong, then the transaction will be rolled back from the external data storage. But the idea is that you can't get a situation when either like information is committed into Ignite but not to external storage, or the other way, or like one node commits something, another not. All these cases are supported and the correctly handled. And now it's time for a demo. The idea behind this demo will be like how to start working with Apache Ignite if you have a database in Postgres. So I have a Postgres database that I downloaded from the internet. There is a sample database with cities and countries. Yeah. Oh, yeah, sure.
So, two-phase commit will fix the problem of fixing either the whole committing the whole transaction or not.
Yeah.
But it does not guarantee that all legs of the same transaction will be committed at the same time. So it will still open up some holes where you can see data committed on one node, but not on the other node. So a query which comes in between the second phase of the commit will still see some inconsistencies in the data. How does Ignite fix those?
No, it's actually not true, because the entries that are committed, that participate in the transaction, they are locked by that transaction. And until you commit the transaction, the query won't be able to get information from it. So if the transaction is ongoing, if the commit phase hasn't completed yet, then you won't be able to access this data because it's locked. And yeah.
But PostgreSQL has MVCC, which won't keep the data locked.
Yeah.
It will still give the older versions away.
You mean it's like possible to get, if you read both Postgres and Ignite, then it's possible to get different results, so like under race condition.
Yeah.
Well, yeah, usually it's the access is done from one point. Like if you access only Ignite, then it's impossible to get any inconsistencies because there's a single entry point. It's rare when you need to access both, like caching layer and the Postgres itself. Usually the migration happens to the system, like to the caching layer in the first place.
Okay. And going back to the grid, like where you showed multiple Ignite clusters.
Multiple, well, it's not.
Yeah, the middle grid.
In the middle, there is a grid. Yeah, there are multiple nodes.
The middle section
in
that diagram. So is it multiple Postgres instances or it's?
No, the Postgres instance is on the right. It's like a single Postgres. You can have multiple Postgres instances, but within a single transaction, you can use only one. That's like a limitation. Yeah, you can configure different integrations with Postgres, but well, within one transaction, you'll be able to use only one of them. And in the middle, there are like Ignite nodes. Those are not Postgres.
Yeah, so when those different Ignite nodes connect to the same, under the same transaction, the Postgres
no, it will be the connection will be done actually by the coordinator. A single transaction will be opened in Postgres. All right, we're running out of time. Actually, let's go to the demo. So that's the data set that I found on the internet. That's cities and countries. It's actually small. I'm not going to show how it will boost your performance. I would like actually to show how it's easy to start working with Ignite. So here are like 3 databases. Okay, can you see what's written there? I can increase the font here. So yeah, there is some data in city table, for example. Yeah, from city. Yeah, there is some information about cities. There are name, country, district, and population, and ID. And for countries, there is also some information that we are going to pull into Ignite and start working with that. For that, there is a tool called Web Console. I deployed it locally on my laptop. It's actually available by the link console.gridgrain.com. It's like the same thing, but I wasn't sure that I would be able to access internet during the presentation, so I just deployed it locally. There is a possibility to install it on premises, so just on your laptop or somewhere in your infrastructure. So there is a functionality to import the database. Here you insert, you put some credentials to your database that you want to import. You just click next, select the schemas that you want to import, and yeah, there is some configuration. If you don't want to, if you just want to try out Ignite and don't want to read about that, you can just keep it as it is. But there is a possibility to configure things that will make you achieve the performance and the guarantees that you need. So we're going to have the cluster here in the configurations tab. And yeah, I'm not going even to change anything. You can go through the configurations that are imported from Postgres and to tune it somehow. But yeah, it's not required for the first try. You can just click Save and Download, and after that you will be able to unzip it and import that project. And a Maven project will be generated, and you will be able to open it in your IDE and work with it. I did that before the presentation. I'm not going to wait while the IDE is doing the import. That's the thing that I just downloaded from Web Console and extracted it. The only thing I changed here is in resources, in the secret properties, I changed these properties to make the connection to the Postgres installation. And yeah, I put the JDBC driver for Postgres into the JDBC driver directory. There is a README that tells you what to do, so you won't be lost while doing that. There are some auto-generated classes and configurations. What you can read through is like the XML configuration of Ignite. I didn't change a single line of it here. It's like it configures the connectivity between nodes if you start more than one node, and configures the connection to Postgres that you can specify in the properties file. So let's start a few nodes here. Yeah, I'm going to start 2 nodes just on my laptop. It's running from my IDE, and we can see that 2 server nodes are running. And now we can go to the load package and start loading the data. There is some code that's calling the load cache function that's pulling the data from Postgres and saving it in in Ignite. So we can see that all the import is finished. And now we can go to Web Console. You can see that it found my cluster. And you can see some metrics, for example, in the monitoring dashboard. Here you can see that I have 2 nodes, and there are some caches configured with the names. But here what we're going to do is run some SQL queries on that cluster. Now, I prepared some queries to run on the cluster. Here we are looking for the most populated countries with this select. You can execute it either in Postgres, in Ignite, it will be the same. So these are the results. The query is split into actually 2, sent to both nodes. The map requests are executed there, sent back to the reducer, and the result is aggregated. So this is the result of this execution. If you can do the same from console GridGrain.com, that's deployed into cloud, and you'll have the same like behavior. You can, for example, see that you can change something in Ignite. For example, there is this record, which is also available in Postgres. You can find it here. And for example, if you want to change something in that, I can do an update query, and it will lead to a syntax error. Yeah. All right, something's missing here. Well, that's a pity. That's awkward, sorry. All right. You can see that the population changed. And if you go to Postgres, it also changed in Postgres. So right through semantics is achieved. If you change something in Ignite, it's also changed in Postgres. And you can also like delete, insert new entries. They will be propagated to the Postgres. So yeah, that's actually basically it. So thank you. Now I'm ready to answer your questions. Yep.
So if we are using Apache Ignite, we essentially have to use double the RAM, right? Because we will allocate RAM for Postgres as well, and then for Apache Ignite as well. So why not use a solution, for example, Citus, and keep the whole Postgres into memory, and just then we'll have the advantage of distributed SQL as well, and we will be able to run using memory also.
Well, in this case, you'll still have the like disk-centric solution. You can't.
But we can run it in memory, right?
As far as I know, you can't really configure the Postgres to keep everything in memory. Some work, you'll need to do some initialization to pull everything from disk from start, or somehow configure the ratio between disk capacity and memory properly. It's it's doable. Yeah, that's a valid replacement, and
So what will be the pros of using Apache Ignite in that case?
We see in Apache Ignite is purely in memory, so there is no chance that you will go to disk and get a latency spike. And Postgres, it's highly configurable. It's like very flexible, and it's often hard to find the proper configuration that will make your system work perfectly. So with Apache Ignite, I think that's easier achieved.
And Ignite is database agnostic, so we can use it with another database as well, like MySQL.
With MySQL, with Oracle, with any external database.
Just one more question. If we have a data skew, for example, we have a lot of data in a table, which we want to be stored in disk. So can we configure Ignite so that only the tables which are smaller, on which we want faster querying, goes through Ignite? And
sorry, Mr. Where do you have the data?
Data skew. So, for example, one table is pretty large, which we don't want to be loaded into memory. So we want faster querying on a few tables. For that, can we use for just those? Can we use Ignite? And for the rest of the tables, can the queries directly route to Postgres?
All right, that's a good question. There is a possibility to change the ratio between different data regions in Ignite. So, for example, you can allocate like a huge data region for some certain caches in Ignite, and a smaller data region for external ones. So you won't be storing all the data cached in the whole memory set, but you can configure how much of which.
But can I put a hard limit that this table doesn't need to be loaded into memory? It should stay in Postgres and doesn't need to come on Ignite.
Well, in this case, you can actually use Postgres directly if you don't need to.
But I have a few tables which need to be. Okay.
Any general questions? Other than that?
Yeah, I think we can continue.
Thank you. Thanks, Dennis. Thank you, everyone.